multiply by hc, and here comes your Compton scattering formula. Which I told you. Now, this derivation, as nice as it is, means nothing unless you observe it. And so the Compton scattering is one of the classical experiments that can be carried out. It's not very complicated to set up and do the measurements. And you actually do get this relationship between the shift in a frequency, in a shift in a wavelength of light scattered with the electrons. So, provided that this h is precisely about 6 times 10 to the minus 34. Joule seconds. It's interesting, for example, to determine what is the value of this quantity, which happens to be known as a Compton wavelength. I'm not going to be very precise because h is what, 6.3 something, right? I never remember. Huh?
66.
I know it's 6 times 10 to the minus 34 close enough. So h is on the order of 6 times 10 to the minus 34 joule seconds. Mass of the electron is about 9.1 times 10 to the minus 31 kilograms, right? And C is 3 times 10 to the 8. So for the electron which participates in this Compton scattering, H over MC is something like 6 times 10 to the minus 34 joule seconds divided by 9 times 10 to the minus 31 kilograms times 3 times 10 to the 8 meters per second. So 6 divided by 27, that's about quarter, right? Or maybe 1/5. It's between 0.2 and 0.25. So this is something like, say, 0.2, maybe 0.25,
0.222.
Huh?
0.222. Because it's 2 over 9.
Yeah. But remember, this is not really 6.
Yeah. It's around that.
Yeah. Close enough. So you have 10 to the minus 34 and 10 to the minus 31. It gives you 10 to the minus 3, right? 10 to the minus 3 and 10 to the divided by 10 to the 8 will give you something on the order of 10 to the minus 11 meters. So that's something like the size of an atom. Now let's calculate Compton's wavelength of any monoliths. Okay. To round it off, let's take a person that has a mass of 100 kilograms. It's just 10 to the 2, it's easy to count. So you have 10 to the 2 times 3 times 10 to the 8. That will be 3 times 10 to the 10, right? So you have 6 divided by 3, which is 2. So you have 10 to the minus 34 divided by 10 to the 10. It will give you something like 2 times 10 to the minus 44. Unobservable. So for something which is macroscopic, I mean, whether you take 1 kilogram, 100 kilograms, or even 1,000 of a kilogram, doesn't really matter. You are still in 10 to the minus 30s and 40s in terms of the meter. Unobservable. So, somehow it seems that objects are sufficiently small. It's when quantum mechanics matters that objects are classical big. Okay. quantum mechanics doesn't matter. Bohr's model of atom I'm not gonna spend any time on, and you are supposed to do that essay on Young's experiment using finite lectures notes, so I'm not gonna dwell over there much either. Now, all of these developments led Louis de Broglie to make a proposal. If you need to treat an object quantum mechanically, then this is what will hold true. And these are called, yes?
I just want to mention, you know that clock doesn't work, right?
Yeah, I know, it's
Okay.
9 something.
18.
Huh?
18.
Are we overtime?
Yeah.
Why should you tell me?
I'm on a roll.
Okay, so the last thing, so this is what Louis de Broglie said. For photon, he knew this was true. This came from the Compton experiment. He said, also true for the particle of mass moving with velocity v such that momentum is mv. So he said, what works for the photon should also work for the particle. And that this became interpretable just like this. If you relate this to the wavelengths, then you can think of combining these two into what is known as a dispersion relation. Lambda nu is c is the same as writing nu is c over lambda, and then you multiply by h. This would be energy is p. This is true for photons. For particles, the same thing is true, because you can write energy as p squared over 2n is h nu. And so this is interpretable in the same way, according to de Broglie, as a dispersion relation for the particle. And he says, use this, and you'll get a quantum mechanics for particles. Now, what happened is that Schrödinger knew some of that, then he heard Heisenberg talk, and he told him, you have another eigenvalue problem, and he wrote down the equation, which was then always known as Schrödinger equation. Okay, so we'll talk about that next time. Stop me if I go over time.